Hi everyone, and welcome to this video on the Evoformer in AlphaFold. I'm Killian Manton, and this video is the fifth in our series where we'll be implementing AlphaFold from scratch. The Evoformer is the biggest component of the model in terms of parameters. The full model will have approximately 93 million parameters, and the Evoformer accounts for 88 million of them. We can infer from the attention weights in the Evoformer's final layers that it already has a solid grasp of the protein structure. The heat maps at the bottom reveal which residues were used for the attention update, and the attention pattern looks strikingly similar to the pairwise distances that appear in the model's final prediction. The structure module that follows the Evoformer then translates this concept into actual predicted atom coordinates. The Evoformer consists of several identical blocks using attention as its core mechanism, somewhat like the transformer architecture we've seen in the video on attention. Still, its architecture is a little more elaborate, and we'll go through it step by step. In the last video on feature extraction, we already made a quick glance at this diagram. With feature extraction, we managed to create the four tensors on the left: the extra MSA feed, the residue index, the target feed, and the MSA feed. Now we'll be skipping over everything in between and jump directly to the Evoformer. We'll cover the input embeddings in the next video. This is because the extra MSA stack, which is part of the input embedder, is actually just a smaller version of the Evoformer, so it's easier to learn it this way around. If you feel like you can't wait that long, here's a super quick rundown. The linear layers should be nothing new to you. Outer sum is just like the outer product, only with plus. Rel pos is the way that AlphaFold handles positional encodings. We don't directly replace the indices with learned vectors, but for each pair of residues, we take the difference of the indices and replace that with a learned vector. The tiling of target feed just means broadcasting it to the bigger shape, and the two R's next to the pair and MSA representation show where the recycling embedder takes place. AlphaFold runs its whole architecture several times, and the recycling embedder uses the outputs from the last iteration to update the pair and the MSA representation. If you want to, you can pause the video and check if all of that makes sense to you. That way you can watch the next video on double speed. But for now, all you need to know is that after feature embedding, we end up with a pair representation of shape RRCZ and an MSA representation of shape SCRCM, with R being the number of residues in the protein, SC the number of sequences we selected as cluster centers during input embedding, and CZ and CM the embedding dimensions of the representations. Like a transformer, the Evoformer consists of a number of identical blocks, and each block looks like this. It works on the MSA representation and the pair representation and transforms them to outputs of the same shape. It is split up into an MSA stack, the top row, and the pair stack, the bottom row, with two information channels between them. The basic idea of the Evoformer is this. We want to do attention on the inputs, but they are just too big to do a full attention mechanism. Imagine us working with a protein that's 400 residues long. The pair representation would then have 160,000 entries. That's an incredibly big sequence length for attention. In comparison, the standard GPT-4 model has a context window of 8,000 tokens. With attention having squared memory demand, we need 102 gigabytes of graphics memory just for one attention module. So, knowing we can't do full attention, AlphaFold uses either row-wise or column-wise attention. For 400 residues, that would mean we'd need 400 squared floats in the attention scores for each row, and 400 to the power of 3 in total. These are around 256 megabytes for one attention module. We can see how AlphaFold uses this in the flowchart for the Evoformer. The MSA stack consists of row-wise attention that uses the pair representation as bias in the attention mechanism, column-wise attention, and a transition, which is just a two-layer feed-forward net. Outer product mean is what it says, an outer product along the residue dimension and averaging out the sequence dimension, to get the MSA representation to shape RR so that it can be added to the pair representation. The modules in the pair stack look a little stranger. The two attention blocks, triangle attention around starting node and triangle attention around ending node, are basically row-wise and column-wise attention as well, using the pair representation itself as bias. The name triangle attention comes from a cool interpretation of the entries that explains the use of the bias as completing the third edge of a triangle in a graph. We'll look at that later. The two triangle updates before it are row-wise and column-wise sum products with the same triangle idea, and the transition module is a two-layer feed-forward net again. Lucky for us, our multi-head attention implementation already supports row-wise and column-wise attention. All we need to do is specifying the attention dimension for the module correctly and constructing the biases where needed. But before we start with that, let's briefly recap attention. For gated self-attention with bias, we compute 4 linear embeddings from our input sequence: the key, query, and value embeddings, and the gate embedding. We compute the scaled dot product of each query with each key, add the bias, and use softmax to normalize the attention weights. Then, for each query, we scale the value vectors by the according attention weights and add them up to get the intermediate output. This is multiplied against the gate embeddings, which are normalized to the range 0, 1 by sigmoid, and passed through a linear layer to get the final output. In this notation here, a linear layer going from Ci to Hc means a linear layer going from Ci to H times C, followed by reshaping the output. So, if we wanted to do attention on the MSA representation, for example, we'd first need to select the input sequence. If it is row-wise attention, the input is just one row of the representation. As we saw, the row-wise attention in the MSA stack uses the pair representation as bias. That works pretty well because the shapes almost match. We only need to use a linear embedding to transform the channel dimension to the attention head dimension of the multi-head attention module. If you're wondering, the reason why the bias looks like it has more dimensions than the pair representation, it's because I only used the staggered map visualization to represent the different heads. In the pair representation, each colored square represents one vector, while in the bias, dot product affinities, and attention weights, each square is only a single number. That means the pair representation and the bias both have 3 dimensions and everything works out nicely. So, let's see how this looks in code. This is pseudocode from the AlphaFold paper for the row-wise gated self-attention with pair bias module. You can find it in the supplementary information of the paper. The code starts with a layer normalization of the MSA representation M. Line 2 and 4 create the query, key, value, and gate embeddings for the attention mechanism. In line 3, the pair representation is turned into the bias, using layer normalization followed by a linear layer to transform the channel dimension into the number of heads dimension. Note that B is the only letter here that's not drawn in bold. That's because the entries of B are single numbers, while all other symbols here represent vectors. In line 5 and 6, we've got a mathematical formulation of a row-wise attention mechanism. You can see that it's row-wise because the row index, S, is just being carried along for the queries and keys in line 5, as well as for the gating, the attention scores, and the value vectors in line 6. The column index on the other side is where the attention mechanism happens. It's the I index of the queries and the J index of the keys, showing how they act in an each with each fashion during multiplication. And it's also the index along which the softmax function does the normalization. In line 7, the outputs from the attention heads are concatenated and passed through the output linear layer. These steps should look like the attention flowchart we just went through, even though the notation might look a little odd. But when you're doing the actual implementation of this, you won't need to spell this out as code, given that we already implemented the attention mechanism. The actual Python code will look more like this. The first 2 steps are identical to line 1 and 3. Moving the axis in the bias is more of a technical problem. In our attention implementation, the number of heads isn't the last dimension, but the third from last. For the real attention mechanism, all we need to do is pass M and B to a multi-head attention module that had the attention dimension correctly specified during initialization. Note that for row-wise attention, we need to specify the column dimension as the attention dimension, as it is the index that is actually cycled through during row-wise attention. Just like how when summing up the individual rows in a matrix, the dimension along which summation happens is the column dimension. The column-wise attention function looks mostly like row-wise attention. We don't even have to prepare a bias here. You can see that it's column-wise this time in line 4. The column index, I, is kept as is during the attention mechanism, while the each with each vector multiplication of the keys and queries happens along the row dimension, denoted by S and T respectively. Line 5 is the only time that the pseudocode in this series will deviate from the code in the AlphaFold paper without it being a typo by me during typesetting. In the paper, the indices for V in line 5 are ST instead of TI. I'm pretty sure I did it correctly, but I'm a little afraid of going against the paper by DeepMind, so I'd be glad to hear your opinions on that if you have any. The last part of the MSA stack is the MSA transition, and as I said, it's just a 2-layer feed-forward neural net with layer normalization at the start. It goes to a higher dimensional intermediate with 4 times the dimensions before going back. Such a feed-forward block is typical for transformer networks, including the number 4 as a scaling factor. With that, we covered the 3 modules from the MSA stack. It's connected to the pair stack by outer product mean, an operation that's designed to reshape the MSA representation to the pair representation. There are 2 things to note in this code. First, the outer product is not calculated between M and itself, but between 2 linear embeddings A and B of M. This increases the flexibility for the model to bring meaning into the outer product. The second thing to note is that we are actually calculating 2 outer products here. The first one comes from the way A and B are indexed. The column index of A is I, and the one of B is J. This means we have an each with each calculation of the tensors, and it's what creates the desired shape. The second outer product is along the channel dimension, and it's denoted by the cross operator between the vectors. The different channels of the tensors are multiplied each with each as well, expanding them to C by C or C times C after flattening. The row dimension is contracted by taking the mean, and the C times C channel dimension is brought down to CZ by a linear layer. Line 3 might look a little convoluted, but it's just a linear operation again, and that makes it a perfect candidate for our trick of just designing einsum expressions that fit the dimensions. In Python, the method looks like this. In the einsum expression, the row dimension is contracted, while the column dimension and the channel dimensions are broadcasted to create the correct output. However, there's an actual difference between the Python implementation and the pseudocode. Feel free to pause the video and see if you can spot it yourself. Our einsum expression simply summed up along the row dimension, but the pseudocode tells us to take the mean. We divide by the number of sequences, but we do so after the linear out layer, not before it. That's not a big difference, but it is one. Concretely, it additionally divides the bias of linear out by the number of sequences, compared to what you had if you did it before the linear layer. This shouldn't have a big impact, and the model would probably train just as well using the operation like it's written in the pseudocode. But we don't train the model, which means we have to stick to the actual implementation so that the pre-trained weights work for us. With outer product mean, we arrived at the pair stack. As we noted earlier, most of the modules in it start with the word triangle, and we'll look at why that is before going into the individual algorithms. To understand the triangle mechanism, we need to think about what the representations might actually encode. For the MSA representation, this is pretty straightforward. We've got the different source organisms for one dimension and the different residue positions as the other, so each vector might carry information on a specific residue in a specific protein. If we have operations that are row-wise, we have crosstalk between the individual positions, but for each of the organisms in isolation. Column-wise operations allow looking at information at the same position, but over different organisms. It's pretty clear why this type of information flow might be helpful for structure prediction. However, if we go over to the pair stack, things aren't that clear anymore. As its name suggests, we hope that the individual entries carry information on the interaction between pairs of residues. In fact, we have 2 entries per pair, the entry ij and the entry ji. With that, we could think that one of them, ij, carries information going from I to j, while the entry ji carries signals from j to I. For example, you could envision a glutamate telling a nearby glycine it's negatively charged, and the glycine sending back that it doesn't care because it's neutral. Of course, this is all theoretical. The actual values of the entries just arise as learned features, and their semantic meaning is poorly analyzed. Still, AlphaFold was highly successful, so it's a good idea to pay closer attention to the theory behind its architecture. With the interpretation that the entries carry information on the directed interaction between 2 residues, let's look at how an update, like an attention update, would play out. Let's say, for example, we wanted to update the pair ij from the pair ik. This is called an outgoing update, or an update around the starting node. Since the first index, I, is fixed, this corresponds to row-wise operations, like row-wise attention or a row-wise multiplicative update. The authors from AlphaFold suggest that in this situation, it's important for the model to have information from the interaction between j and k to complete the triangle. If the entries carry information on the distance, for example, it's necessary to also take the distance between j and k into account, so that we don't end up violating the three-dimensional structure, maybe by violating the triangle equation on the distances. The choice between jk and kj is a little arbitrary, but given that we are updating ij, AlphaFold uses jk in the spirit of outgoing edges. We can do everything just as well for incoming edges, also called updates around the ending node. Here, we want to update ij based on kj. Since the column index is fixed, this corresponds to column-wise operations. Just like before, the authors suggest that it's beneficial to also take the values from ki into the equation to complete the triangle with the last incoming edge. With this theory, let's look at the pair stack. We can see that the first and third block are using outgoing edges or attention around the starting node, which we identified as row-wise operations, while the other triangle updates use the incoming edges or attention around the ending node, which are column-wise operations. The multiplicative update starts with a few steps to create two embeddings A and B from the pair representation. They are computed as a linear embedding times a gate-like linear sigmoid embedding. The module also creates an output gate G that's multiplied against the layer's output. The interesting operation happens in line 4, where there's actual crosstalk between the positions. Here, using outgoing edges, we want to calculate an update of the entry ij with the information from the outgoing edges ik for different k. Our thoughts on triangular attention suggest that to do so, we need to take jk into account as well. The way this is done here is by multiplying the vectors aik and bjk pointwise before summing them up. This summation is followed by layer normalization, linear layer, and multiplication against the gates. We do basically the same thing in the incoming updates. Highlighted in yellow are all the differences to the algorithm we just saw. Here, to compute the update for ij, we want to look at the other incoming edges kj. To complete the triangle, we also consider the entries ki, and the concrete operation is pointwise multiplication of the two columns, followed by summation along the row dimension. Here, you can see the two algorithms side by side and look at what makes them different. Using outgoing edges, we operate on two different rows, aik and bjk, while for incoming edges, we operate on two columns, aki and bkj. After the multiplicative updates, the next part of the pair stack is attention, around the starting node and around the ending node, which basically means using outgoing edges and using incoming edges again. Looking at the code for attention around the starting node, this is simply row-wise attention using the pair representation itself as the bias. In line 3, we can see how we're using the same trick we used earlier to turn the channel dimension into the number of heads dimension for the bias. This use of the bias fully aligns with our theory on completing the triangles. The update for the entry ij corresponds to the query qij. It can get updated by all the different keys kik, which are outgoing edges from I. But the attention score that's computed for the key ik is influenced by the bias bjk, which is the third edge in the triangle. Attention around the ending node is basically the same. The differences to the previous algorithm are highlighted in yellow. This time we have column-wise attention, again using the pair representation itself as bias. But this time we transposed the bias. You can tell from the indices in line 5. The column index j is fixed for q and k, as it should be for column-wise attention. Using the query index as the first dimension and the key index as the second dimension of the attention scores have the indices in the order ik. B, however, is indexed as ki, which means that when going to PyTorch, we need to transpose it before adding it, so that we implement the algorithm correctly. Like in the previous algorithm, the update to ij from kj is influenced by the third edge ki using the bias. The final part of the pair stack, the pair transition, is just a two-layer feedforward module again, just like it was for the MSA representation. Putting all of it together, this is the full code for the Evoformer. The methods in yellow are the AlphaFold specific methods we went through in this video. As you can see, these methods are called in the same order as presented in the flowchart. MSA row attention with pair bias, MSA column attention, MSA transition, outer product mean to go over to the pair stack, then in the pair stack, outgoing triangle multiplication, incoming triangle multiplication, attention around starting node, attention around ending node, and the pair transition. Aside of the calls to the submethods, there are some other implementation details we can see here. As we discussed earlier, the Evoformer consists of multiple identical blocks, 48 in fact, and each with its own weights. The row-wise and column-wise dropout can be safely ignored. Dropout is a form of regularization that's used during training. It randomly sets some values to 0 while scaling the other ones up so that they have the same expected value. AlphaFold uses dropout setting whole rows or columns in the representation to 0. But we aren't training the model and dropout isn't applied during inference, so we don't have to worry about it. One big detail to note is that we don't set the outputs to the results of the operations, but we add them to the inputs. These are the so-called residual connections we talked about in the part on attention. Residual connections make training way more stable. If you think of an operation like the multiplicative update, where we just took 2 rows in the full tensor, multiplied them and summed them up to generate an output, you can imagine that this would be a pretty transformative operation without residual connections. With residual connections, the model can just learn small weights for the embeddings and generate an output close to 0. That's more like an offset to the input than a complete substitution. Finally, the Evoformer ends off by taking the first row of the MSA representation and passing it through a linear layer. This is the so-called single representation, and it's the only part of the MSA representation that goes on from the Evoformer to the structure module. The rest of the MSA representation is dropped and won't be used by the model anymore. It's somewhat like in our sentiment analysis implementation in the notebook on attention, where we only kept the output from the first token for classification, and the model needs to learn to aggregate the information into that. If we think back to how we constructed the MSA feature, the first row in it came from the actual target sequence, so it makes sense that this is what's living on. So, quickly going over the full architecture again. The Evoformer is built up by a number of identical Evoformer blocks. Each block consists of an MSA stack and a pair stack, with 2 channels of information in between. The MSA stack consists of 3 modules: row-wise attention using the pair representation as bias, column-wise attention, and a transition module that's just a 2-layer feed-forward net. The MSA representation is reshaped to the shape of the pair representation by outer product mean, taking the outer product along the residue dimension and averaging out the sequence dimension. This is added to the pair representation for information flow from the MSA representation to the pair representation. The pair stack itself consists of 2 multiplicative updates, 2 attention updates, and another transition module. The multiplicative updates are computed as the sum product of 2 of the rows or 2 of the columns respectively, and the attention updates are row-wise attention using the pair representation as bias, and column-wise attention using the pair representation as bias as well, but transposed. With that, we are done with the Evoformer. Compared to an architecture like the transformer, it's a bit more involved, but I hope I could convince you that the individual steps aren't that complicated. Using attention only row-wise or column-wise is a straightforward solution to a tensor that's just too large. The triangular attention mechanism is arguably clever, but maybe you could have come up with it by accident, given that it boils down to just using the pair representation itself as bias. In the description, I linked a tutorial notebook where you can do the full implementation of the Evoformer yourself with automatic checks. In the next video, we'll close the gap that we left between feature extraction and the Evoformer. Until then, good luck with the notebook and happy coding!